Okay, so we are up here and live. Just want to say that we appreciate your time, Brian. I guess real quick, if you could just if you could just tell us a bit about yourself and your background, and what is one of your favorite things about the state, and what it has to offer, as a personal question. Take it away.
Okay, yeah, thanks for having me. My name's Brian Shaw. I'm a geodesist with the National Geodetic Survey, and I recently got the position of the Rocky Mountain Regional Geodetic Advisor. So I help to provide geodetic expertise to Colorado, Wyoming, and Montana. And so I've worked at NGS for 18 and a half years now. And I've been in the IT, I've been in our geodetic services division, and now I'm in a new role with the advisor position. So I had been in Silver Spring up until this last June, where I moved to Colorado. I grew up in Colorado Springs when I was young. So my dad was in the Air Force and lived there for most of the 80s. And so I'm happy to be back in Colorado. I guess my favorite thing about Colorado is I really like the Front Range. Growing up in Colorado Springs with Pikes Peak there, living on the plains, I just really liked the weather and how you could smell the rain before it came up over the Rockies. And so Colorado's my favorite state, so I'm happy to be here and happy to be back. And with that, I'll hop off the video and go right into the presentation, if that's all right. So, thanks again for having me to GIS in the Rockies. I've attended and presented at this conference quite a few times over the last, 5 to 10 years. Normally I've been traveling, having an excuse to come out to Colorado from DC. So it's nice to actually be here, although doing it virtual, I get to do it from the comfort of my own home. I'm here to talk to you today about the Modernizing the National Spatial Reference System. Hopefully this isn't new news to you guys, because we've been doing our best to inform everyone and let everyone know that this is coming. Our plan had been to modernize it in 2022, but with recent things like the furlough last year and the current situation today, a lot of the data we've been collecting has caused that modernization to have to be pushed back to about 2024, 2025. So, but we are doing our best, and we want to make sure we do it right when we roll this out. So with that, I'll hop right in. Wanted to make some of the resources we've done, we made aware, we put out to the public. So we have a NGS training center down in Woodford, Virginia. We do leveling training there. We do Opus projects training, some astro training. So there's quite a lot of training, in-person training done there, as well as virtual training done. We've put out many education videos, which you can find at this link. We put out a monthly webinar series, occasionally more than one in a month, but usually it's just one in a month. We've done several geospatial summits, and the last one held last year, we recorded all of the sessions, and those recordings are available at that site. And then all of the presentations that that our employees give, we put up in our presentation library and make that accessible to people. So you can go there and download presentations and even use those slides, because we're federal employees, those are public domain. So again, this presentation will be there at that presentation library for you to get access to these links. One of the things I wanted to highlight is the importance of coordination. So when we're modernizing the National Spatial Reference System, you know, this requires a ton of communication and coordination with our constituents. And so we have 4 geodetic advisors throughout all of the US states and territories. And these geodetic advisors work with coordinators in each of the states. So we, you know, working with multiple states, you know, I'm fortunate to have the best region in my opinion, and only 3 states. So it's easier for me to know the right contacts, but my coworker, Dan Martin in the Northeast, you know, he's dealing with, you know, 8 or 9 states. And so he's got to work with that many different state governments. So having these coordinators really helps us to understand things going on at the state level, keep, you know, have communication with them to know things that are coming up or any of their needs. And so this coordination is very important for having a communication from the state or even county level up to our federal level to make sure that we're helping to meet everyone's needs. And so a little bit about NOAA and NGS. NOAA was the first civilian science agency. We were first created as a survey of the coast under Thomas Jefferson. And so the importance of this was back when our nation was new and blossoming, you know, almost all of our commerce came through shipping. We had tons of farmland and farmers, and we'd export a lot of these goods around the world. And so shipping was extremely important. And back then, you know, to have good ports and good shipping, you really needed to know the bathymetry of your coasts and your ports so that there wasn't shipwrecks that would ruin things. And so to do this, Thomas Jefferson created the survey of the coast, but really to understand where those offshore obstructions are, you really needed to know where onshore positions were, so that you could reference those offshore seamounts or coral reefs or whatever and understand their position relative to the land and the ports. So that's where geodesy really came in, and when we became the US Coast and Geodetic Survey. And so Ferdinand Hassler became the first superintendent. He really helped to instill a lot of the science and surveying and geodesy of our agency that really found the way. And so we were, for a long time, we were the US Coast and Geodetic Survey. And then in 1970, NOAA was established, where lots of these science agencies, the US Fisheries, the US Weather Service, the US Coast and Geodetic Survey, a lot of these were all packaged into one bureau called the National Oceanic and Atmospheric Administration. And so NGS's mission today is to define, maintain, and provide access to the National Spatial Reference System to meet our nation's economic, social, and environmental needs. And so what is the National Spatial Reference System? The National Spatial Reference System is a reference system that allows you to have consistent coordinates and to help us to define latitude, longitude, height, scale, gravity. And so when you're referencing data to other data, you really need to make sure you're in the same reference system so that you're comparing apples to apples. You know, you don't want to have coordinates in one datum and coordinates in another datum and start doing spatial analysis where, you know, for any of us GIS users, you know, when you've added data layers in and the things just don't line up right, that's often been a datum error, or not a datum error, but just 2 data sets in different reference systems. So they don't properly line up, or maybe someone had used imagery in one reference system to digitize, but they thought they were in another. And so then that would be kind of a datum error. So having these consistent coordinate systems is very important to assure that the analysis we're performing is correct. And then the decisions made from that analysis are appropriate. And so what is the importance of geodesy? Well, geodesy has been very important, as I mentioned, to our ports and understanding where the offshore obstructions are, but also just understanding where different locations are and getting a more accurate position for locations. So on the left here, we have a picture of Hassler's first survey in the New York City area. In the middle, we've got one of our, back when we were still doing triangulation, setting up Bilby Towers and doing the kind of legacy surveying with theodolites. So you can see these triangulation networks. And then on the right here, you have the GPS baselines from GPS. So GPS has really revolutionized surveying. And then again, today we also put out bathymetric maps. So our sister office, the Office of Coast Survey, puts out these bathymetric maps that really help mariners and anyone going out on boats to know where it's safe for them to travel, to know where these obstructions are. And so why do we do what we do? Well, the Earth is infinitely complex. It's very hard to model such a complex thing as the Earth and get an accurate model that really models it, to a very accurate and precise means. And so in the past, we've generalized the Earth as a sphere. As science progressed and more measurements were done, we learned that it's not actually a sphere, it's an ellipsoid. And in that, it's actually an oblate ellipsoid, so it's pinched at the poles. And even that isn't quite right. The Earth is not a perfect ellipsoid or anything. It's, it bulges here and there. We've got oceans for 70%, 70 or 80% of the Earth's surface, and a lot more of the land mass is in the north. So it actually bulges in the southern hemisphere because the southern hemisphere is mostly ocean. So there's lots of science that goes into this modeling, and the way we've kind of represented what we call sea level to determine an elevation is using what's called a geoid. And so the geoid takes into account the masses of the Earth, the land masses, the masses under the ocean, and it creates this geoid, which is a general representation of what sea level would be around the world. And so our job at NGS is to create the geoid model for the US states and territories. How we're doing that moving into the future is primarily through gravity. And so gravity is fundamental to positioning in the world. Every surveying measurement relies on gravity in one way or another. From when you're setting up your survey equipment with a bubble level, you're getting it equalized to an equipotential area at that location, as well as we're going around and doing aerial gravity surveys to help us to modernize to the new National Spatial Reference System. And so gravity's been studied through history from Aristotle to Galileo to Einstein. And so we've continued to progress and understand more and more about gravity. But up until recently, we actually had never even measured a gravitational wave until I think it was about 7 or 8 years ago. I forget the group that did it, but they actually measured a gravitational wave in 2 different locations that proved Einstein's theory of general relativity. And so the way that we're going about measuring gravity, we've had ground gravity surveys throughout all of the U.S., spot gravity surveys, but it really depended on the locations and the topography. And we've also had ship gravity data collections. I forget how many years ago, but they started putting up satellite gravity measurements, and really to help us to get an even better measurement of gravity throughout all of the U.S. states and territories, we started this Gravity for the Redefinition of the American Vertical Datum project. That project was, I believe it was dreamed up in 2006 or 2007. We did our first survey in Alabama in 2008, and I had the pleasure to fly as a gravimeter operator for that survey. And then we've been going through and we've been collecting more and more gravity. As you can see here, all of the green blocks are completed. The orange blocks we're currently collecting in that area, and the white blocks are planned. And so once this is all done, this is the main thing that we need to have done to modernize the NSRS, because we need this gravity to create the North American geopotential datum that I'll talk about in a little bit. So what are datums and reference frames? This has been a question I've asked myself for many years working at NGS, and I understood the basic concept, but it was really hard for me to get a good mental image of it. And so talking to the former director, Dave Zolkowski, he told me, it's really just a reference surface or framework to reference your data to for consistency. And so thinking about that really made me think about back when I was young, when we'd stand against the wall and your parents would measure you, and you'd see how your height changed. And so if you think of that type of thing, as I have here on the right, the surface to which you're referencing to is the surface you're standing on. So, my height would be different if I was wearing shoes or if I was slouching or anything like that. So, you always tried to stand up as straight as you could because you always wanted to be a little bit taller. But if you think about that reference surface, back then I'm pretty sure we had carpet where I was being measured, but if your parents wanted to replace that carpet with hardwood floor, you've suddenly changed that reference surface. And so that's what we're doing with the modernized National Spatial Reference System, is we are changing these surfaces to which you reference your data to, both horizontal and vertical. And so we're not changing heights or moving places left or right. We're just changing the surface to which the data is referenced to. And so that really kind of stuck with me. Hopefully that analogy helps you to understand it. And so, and another thing to understand is that, latitude, longitude, and height, we're often referencing these even though it's a three-dimensional sphere. And so particularly with GPS thinks with X, Y, Z. So starting with a Earth center, Earth fixed coordinate system. So if you think of that, it's got an XYZ from the center of the Earth that does an XYZ, and then we use that XYZ to convert it to a latitude, longitude, height, which it makes more sense to us humans. And so why modernize the National Spatial Reference System? Well, our current models are built on old technology. We, for the first, 180 years of the Survey of the Coast, U.S. Coast and Geodetic Survey, and NOAA, we were doing triangulation with the theodolites to determine positions, and we were doing leveling with geodetic leveling instruments to determine heights. And so once GPS came around, that really revolutionized positioning. We could now get a more accurate position in seconds through GPS than what it took us, weeks to do with the old technologies. And so, but the old technologies were good. They were just very intensive. And, we learned more and more about the Earth. We create very good models for the technology. But now we understand that NAD83 is not truly geocentric. What we believed to be the center of the Earth when that datum was created, we now know is roughly 2.2 meters off, which then propagates to positions on the Earth's surface. As well as NAVD88 relies on marks in the ground, and it's not easily maintained. So right now, for you to get an elevation, you need to have, sorry for these things. You need to have a mark in the ground that you reference your future surveys to get an NAVD88 height. Now, that mark could be in an area that's subsiding or uplifting, or that mark could have just moved. Maybe when I was doing a survey here in Colorado in 2017, we had one mark that was located in an area where groundhogs had actually dug underneath it, and that monument then moved when you stood on top of it. So to have good NAVD88 heights, you really need to have good stable monuments and assure that they're not moving, which many of these monuments were set in the 30s and 40s. And as I mentioned, today's technology requires more accuracy. And so some of the benefits of modernizing the NSRS are it's fast, it's accurate, it's consistent, there's elevations everywhere. This will significantly help for public safety, improving floodplain mapping and emergency route planning, as well as accurate positioning for autonomous vehicles, building information models, and smart cities. And so I've got a little video here that kind of shows the network that we created. And sorry about the lag. That tower you saw there on the left was called a Bilby Tower. And all of these little junctions of these triangles you see, most of them, they had to set up Bilby Towers at each of those junctions to then turn angles to other Bilby Towers. And so this is a vast network that was, amazing amount of surveying and just people power going into this. And here's the vertical network, and every one of these red lines is people walked every kilometer of that performing geodetic leveling. And so in the 30s and 40s, the Works Progress Act allowed the Coast and Geodetic Survey to hire unemployed engineers to help us to densify this network. And so this was a monumental effort over the last 200 years to really create these networks to allow us to have the datums we have today. So I mainly wanted to show that, to show you the amount of work that went in to create NAD83 and NAVD88. So, that was a huge amount of effort. So what to expect moving forward to the modernized National Spatial Reference System. You can see this horizontal shift. And so we're moving to, we understand that the tectonic plates are all moving in different ways relative to each other. And so to properly position with these plates, we really need to have these reference frames for each of these tectonic plates. So you can see the North American plate is going, will be changing from, roughly about a little less than a meter in Florida to, about 1.6 meters up in Washington, and then 1.5 meters, Montana down to California, as well as up in Alaska. Here in Colorado, I believe it's about 1.3 meters. And so, as well as the Pacific is moving much faster than the North American plate. So Hawaii, American Samoa, they're going to be moving, that plate is moving in a much faster way. So those positions will be changing. I forget how many, I think it's centimeters a year, but I believe it's like about 7 centimeters a year that the plate is moving. So to account for these movements, we really need to have a modernized reference system. And so that's why we are creating these 4 reference frames: the North American, Caribbean, Pacific, and the Mariana. That covers all of the US states and territories. And so here you can kind of see what the North American plate is doing. You can see it's kind of rotating in a counterclockwise way down towards California. But you also see California, that part of California that's on the Pacific plate is all moving, very quickly up to the north, to the northwest. Also looking down at the Caribbean plate, it's moving kind of a different way than the North American plate. So having one reference frame for these 3 plates that are moving in different ways is not the way you really want to do this. And so, as well as there's a lot of vertical motion going on. So subsidence from ground fluid withdrawal or sedimentation. There's something called glacial isostatic adjustment, which is where the glaciers compressed kind of more up near Hudson Bay, and now the land is rebounding. And then there's other geophysical phenomena like earthquakes, calderas, and earth tides. Here on the left map, you can kind of see that GIA in the Hudson Bay where it's uplifting at 8 to 13 millimeters a year. In California, we've got groundwater withdrawal in the San Joaquin Valley that's causing major subsidence. You know, the middle image shows a study from USGS where they saw, you know, anywhere from 20 to 24 inches of subsidence in 16 months. And on the right image is a very famous image of, you know, showing 8.5 meters of subsidence in 50 years. There's horizontal and vertical motion due to earthquakes. Again, in California, the China Lake earthquake that happened, I believe, last year, caused 6 to 10 feet of horizontal shift. And then the Puerto Rico earthquake that happened earlier this year caused 16 centimeters of vertical change. And I forget how much horizontal change. One of the ways we're working to help modernize to this new system is GPS on benchmarks for the transformation tool. And so this will help us to create a better transformation tool to move from NAVD88 to NAP-GD 2022. And so we've put out tons of GPS or tons of benchmarks that we could use GPS on benchmarks to help us to create this more accurate transformation tool. Last year we put out Geoid 18, which is the last hybrid geoid, which will provide NAVD88 heights. This model was much better than the previous ones because we'd gotten so much more data. We'd gotten roughly 26% more data than was used in Geoid 12B. So the North American Pacific Geopotential Datum of 2022 is not just a geopotential datum or not just a vertical datum. So what in the past, you know, NAVD88 is a vertical datum. This is also what you could consider a vertical datum, but it's not just that. It includes geopotential. So understanding where water will flow, deflection of the vertical, which also helps you to understand where water will flow, gravity, and the geoid. So this geopotential datum includes many more models in it and covers a very huge area. As you can see, that's the map on the left is roughly a quarter of the Earth's surface. We're also rolling out a state plane coordinate system. I believe John Hunter is giving a presentation on this, so I won't elaborate too much on this, but we are replacing the state plane coordinate system. And so in Colorado, you can see the preliminary 2022 design is, you know, we're working to reduce the parts per million, the maximum minimum parts per million in the states. And so if you compare the left to the right, that's roughly comparing the current to the new, even though the one on the right is a statewide zone that doesn't currently exist for Colorado. Wyoming also. So how can you prepare? Metadata is going to be essential modernizing to the national space, both data collected today and data collected in the future, because this will improve reliability and accuracy of the data to know what datums your data was collected in, as well as how that data was processed. So this will increase the value and usefulness of that data and allow it to be shared with others for them to know how that data was collected and processed. So it's very important to make sure you note the datums and both horizontal and vertical, as well as the geoid models used for GNSS data. Some recent publications that we've put out, the blueprint documents really provide a vast overview of what this new system is going to be like. We are currently working to update these blueprint documents. They should be available early next year. We've worked to try to make them a lot more user-friendly and to really iron down the details, since when these were written, there was a lot of to be determines. And so, as well as a state plane coordinate system, history, policy, and future directions document. And with that, I believe I am done.
Okay, well, we appreciate your time, Brian. Is there any closing points that you would like to make at this time, or any sort of tips?
Yeah, I mean, the main thing is just, I think, making sure you note what datums you're collecting the data in, how you're processing it or transforming the data. If you're transforming it between datums, that information is very important. So
That's right.
making sure to note that, and we are not going to be shortening mountains or shifting mountains. It's just reference surface will be changed.
Well, great. Well, we and again, we appreciate your time and appreciate it very much. Thank you.
Thank you. Thanks for having me.
Yeah, thanks.